Okay, welcome back to the second video looking at complex numbers here, and we're going to step things up a little bit as we start looking at complex polynomials. Okay? In the previous video, we just did some basic algebra with complex numbers, mostly stuff you've probably seen in a previous class, possibly Algebra 2. Now we're going to really step it up to the big leagues and do some higher level stuff involving quadratics and any kind of degree polynomial here. So checking in on the HL syllabus, we are AHL 1.14. We're going to look at complex roots of both quadratic and polynomial equations with real coefficients. We may actually even get to some that have imaginary or complex coefficients and what that can look like. Okay? So let's start with what we know from Algebra 2. Okay? In Algebra 2, we know that if something is a root or a zero of a polynomial, and in Algebra 2, we always did polynomials that have real coefficients, okay? We should know that that complex root also has a little buddy that goes with it in its conjugate, and both of those must be roots of a polynomial with real coefficients, okay? So in Algebra 2, you probably learned that if you have an imaginary or a complex root, you also have its conjugate as a root as well, okay? So what might this look like in Algebra 2? We might be given that 1 plus 2i is the root of this cubic polynomial and be asked to find the other roots. Okay? So the easiest way to approach this in Algebra 2 at least is probably with synthetic division. Okay? So if we take this polynomial and just strip off the coefficients, okay, we put the root in this little box, we can perform synthetic division on this to get a reduced polynomial here. Okay, so we bring this one down, and then we multiply this one by our root, so 1 plus 2i, and we write this in the next spot. Okay, we then add these two lines to give us negative 4 plus 2i, and we simply repeat this. Okay, now this is where it gets a little challenging because we've got a complex number times another complex number, so we may do this as a little side calculation here, given that we'll need to FOIL this out to get our result. So this should give us negative 4 plus 2i minus 8i plus 4i squared, which I believe will be 4i squared. That's going to be a minus 4, negative 8 minus 6i. Okay, so negative 8 minus 6i goes here. We add 11 to that to give us 3 minus 6i. And we know that this should multiply to give us 15, because we were told this is a root, so it has to zero out at the end. Okay? We'll do a little check that that's actually true. So 3 minus 6i times 1 plus 2i. This will give us 3 plus 6i minus 6i. What would that be? That would be minus 12i squared. This clearly simplifies to 15, so that works out as we want. Okay? Now, using this knowledge that our roots come in complex pairs, we can run our synthetic division again with the conjugate of our original root. Okay? And our polynomial will be 1 degree lower, so we'll only have 3 coefficients across the top here. Now, some of those coefficients are complex, but the synthetic division doesn't care, and this second round is usually a lot simpler, where we simply add these and the imaginary parts cancel out, and then finally we get negative 3 plus 6i, which zeroes us out again. Okay? So the question is asking us to find the other roots. Our list of other roots, our first one would be 1 minus 2i, the conjugate of the root we were given. The final root can be found by rebuilding this polynomial at the end. So this would be the constant term in the negative 3. This would be the linear term in the 1x. Okay, and we simply set that equal to 0, and we can find that the real root for this cubic is 3. Okay, so our answer, our remaining roots, we know are 1 minus 2i and 3. Now, there's lots of different other algebra ways you could approach that, but if we know synthetic division, that can keep everything nice and organized and actually make this easier for us. So this brings us on to a very important theorem in math, which is the fundamental theorem of algebra. Again, we should have learned this in Algebra 2, but if we didn't, it simply states that a polynomial of degree n has exactly n roots. Okay, now some of those roots may be repeated, or they may actually be complex, but if you add up the total number of roots, including the repeated ones, you should get the degree of your polynomial. Now, how does that help us? That helps us to know how many answers we need in each problem. Okay? So we'll start off with a nice easy quadratic here as we explore some interesting properties of polynomials. Okay? So we're told that P and Q are the roots of this quadratic, and we're asked to find them. Okay, well, this is actually a nice quadratic that factors. I believe we're on plus 6 minus 2 here. So we have two roots, x equals 2 and x equals negative 6. We'll say P is the 2 and Q is the negative 6 because they weren't specified for us which was which. Okay? We're hence asked to compute the sum of these two things. So the sum of P and Q, so that would be 2 plus negative 6. That would simply be negative 4. And then the product of these two roots, that would be 2 times negative 6, will give us negative 12. We don't really know why we're doing these operations, but we are for now. Okay? When we turn the page, it asks us if we see any relationships between these roots and the sums and products in the original quadratic equation. Okay? So what we're trying to do is compare these answers, the negative 4 and negative 12, to the original polynomial we started with, which was x squared plus 4x plus 12. Okay? And we'll probably see that it looks like the product, okay, is perhaps equal to the c value, and maybe the sum is equal to the negative b value. This is what we might kind of conjecture or hypothesize, given that we had negative 4 for the sum, and that was the second coefficient in our polynomial, and negative 12 was the last coefficient. So that's what we would conjecture, and let's see if that's true by repeating that procedure on a different polynomial. Okay, so this one has a leading coefficient of 2, but we can still factor it. It is 2x and x. It must be a 3 here and a 1 here, I believe. Let's try that. Plus minus, I believe that works out. We'll just give that a quick check. Okay, multiply that out, that will give us a 6x minus 1. Yep, that should all be good. So we get roots of x equals 1/2 and x equals negative 3, and we'll take the sum and the product again. Okay, so the product of these two roots would be negative 3/2, and the sum, that would be 1/2 minus 3, that would be negative 5/2. Okay. So does our conjecture, our prediction still apply? Is this product C and the sum negative B? Okay. The answer is no, okay, and we just need to modify it a little bit. So we need these to be over 2, and where might that 2 have come from? Well, it looks like that was the A value. Okay. So it actually looks like the sum of our roots, okay, is negative C over A, and the product of our roots, I believe, is B, negative B over A. Oop, our sum doesn't have the negative. Let me take that negative off. Sum is C over A, product of negative B over A. Do I have that the right way around? Nope, I have that completely the wrong way around. Other way around. Sum is, that's the 5 over 2. That is the negative B over A. The product looks like the C over A. And this is actually true for any quadratic expression, okay, in the form ax squared plus bx plus c. If the roots in P are Q, the sum of these guys will be negative B over A, and the product will simply be C over A. Okay? Again, two formulas not given in the formula booklet for quadratics that could be useful to remember on an IB exam. Okay? Or maybe not. Maybe the IB gives us something similar or more advanced that we could actually use. Okay? So how do we use these? We can use these to find coefficients in an equation where we know the roots. Okay, so this gives us a quadratic equation, 4x squared plus bx plus c, and it gives us roots of negative 4/3 and 2i. Okay, so we've got the two roots, and one of them is actually purely imaginary. Okay, and you might think that this contradicts the idea that it must also have a root of negative 2i, giving us 3 roots. And the fundamental theorem of algebra said quadratics should only have 2 roots. Okay, well, this is only true if the coefficients are real. Okay, so that conjugate idea is only true if the coefficients are real. Okay, so if we don't have the conjugate as a root, we know the coefficients don't have to be or likely are not real. Okay? But let's see how we can solve this. Okay, So let's go ahead and take the product of these roots. That's usually the easier one. So that's negative 4/3 times 2i, which would give us negative 8/3i. And we know from our formula in the blue box, this should equal c over a, so c over 4. So if we solve this, we get c equals negative 32/3i, telling us that one of these coefficients is actually imaginary. Okay? We can work backwards now to find the sum of these roots. The sum of these roots would be negative 4/3 plus 2i, and we know that should equal negative b/4. Okay? Again, this is a one variable equation. It's very easy to solve it to get b equals 16/3 minus 8i. So this confirms what we suspected, that these two coefficients a and b didn't actually have to be real numbers. They can be complex numbers. Okay? So moving along, we can generalize to a polynomial of any degree. Okay, so we can take this idea of sum and product of roots up to cubics, quartics, quintics, any polynomial we like. And we actually get these formulas in the formula booklet as long as we know how to read what they're telling us. Okay? So they tell us the sum and the product of the roots of this polynomial equation. Okay? That summation is a little confusing as to how it's representing a polynomial equation. So let's just take it and write this out so it looks more like a traditional polynomial. Okay? It says the sum from r equals 0 to n of ar xr equals 0. Okay? So what does that look like? If we substitute a 0 in, we'll get a0 x0 plus a1 x1 plus a2 x squared all the way up to an minus 1 xn minus 1 plus an xn should equal 0. So that's all that summation is saying. It's just a shorthand way to write that nth degree polynomial. Now, what do you not like about the way I've written this polynomial? It's probably that the leading term is actually at the back. Okay? Well, if it's a polynomial, we can just reorder this to simply put it the way we like and get that leading coefficient at the front, and we can even take away the x to the 0 because we know that's equal to 1, and this is the order we like our polynomials in. So if we have it in this order, the formula book that tells us the sum of the roots of this polynomial is given by negative an minus 1 divided by an. Okay? And let's just write this in words. What are these two numbers? Well, the an, that's the leading coefficient. That's the number at the front. Okay? This an minus 1, you can think of this as essentially the second coefficient. So it's not the leading one, it's the one after the leading coefficient. Okay? And the sum of the roots will be negative second over first. Okay? We also get a formula for the product of the roots. This one's a little more complicated. This one can be positive or negative depending on the degree. So it's negative 1 to the n, a0 over an. Okay? So what is the new coefficient we're using here? We're using a0. Okay? This is the last coefficient, or you can think of this as the constant term. Okay? So it's the constant term divided by the leading coefficient, and then this positive or negative 1 depending on the degree. So let's see how we can use those to solve some problems. Okay? So we're given a quartic equation right here. We're told it has real coefficients. That's really important information to us. That tells us that we'll get conjugate pairs for any complex roots. Okay? And we're actually given two of its roots right here. Okay? 3i and 1 minus 2i. Okay? We're asked to find the values of a and b. Okay? Now, giving us these two roots and the fact that this has real coefficients, they're actually giving us all four roots. Okay, so we know the roots are 3i, negative 3i, the conjugate pairs, and then 1 minus 2i and 1 plus 2i, again, the conjugate pair of 1 minus 2i is 1 plus 2i. Okay? And that's what that real coefficients information is telling us. These have to come in conjugate pairs. So if we have all the roots, we can just work on our sum product formulas. Okay, our sum, that's 3i plus negative 3i plus 1 minus 2i plus 1 plus 2i. If we do all that complex algebra, the first two terms actually cancel out. The imaginary parts also cancel out, and we get a sum of 2. Okay, and we know that 2 is equal to the second coefficient divided by the first negated. So our second coefficient in this equation is the a. So this is negative a over our leading coefficient. Our leading coefficient is 1. So we simply get a equals negative 2. Nice, easy algebra solve once we have it set up correctly. Slightly more challenging is the product. The product of these four complex numbers looks intimidating, but if we do this in the right order, it's really not that bad. Okay? So we know that a complex number times its conjugate always gives us a real number. Okay? So we'll kind of group these two together in their conjugate pairs, knowing that the result of each of these should be real. So 3i times negative 3i will give us negative 9i squared, and then this difference of two squares here will be 1 minus 4i squared. This will turn into 9 times, I believe that's 5, so our product here will simply be 45. And using our formula in the red box, we know that 45 is equal to, that's a negative 1 to the power. The power is the degree of our polynomial, which happens to be a 4. And then this should be the last term, the constant, that's the b, divided by the leading coefficient, which is 1. Okay? If you simplify this out, it's very easy to see. The constant term, the b, is simply 45. Okay? So super useful little formulas connecting the sum and products of roots of a polynomial. So let's do some more polynomial work here. We're told that negative 1 is a 0 of this degree 5 polynomial called a quintic, and we're told that that 0 has multiplicity 3. Okay? So if we're keeping track of the roots of this polynomial, we know there should be 5 of them. Okay? We know we need 5 roots. We know that 3 of them will be negative 1, so we're actually only looking for 2 more roots here. Okay? Now the question asks us for a product of linear factors. Okay? So we're actually looking to write this in its factored form, and we know that one of those factors will be x plus 1 cubed, given that that's how you would get a root of negative 1, and the multiplicity 3 gives us that cubing. Okay? So how do we find the remaining 2 roots so we can build the remaining linear factors? Okay? Well, that's just a case of running synthetic division multiple times here. That's the fastest way to get through this or get this polynomial down in degree to the point where we can find the remaining 2 roots. Okay? So we set this up, we drop the 2 down, we multiply by negative 1, that gives us negative 2. We add here to give us 5, negative 5, negative 2. That would be a 2. This would be a negative 11. This would be an 11. This had better be a negative 6, so that can give us a positive 6, and it can 0 out for us there. Okay? So that shows that negative 1 is a root once. We should be able to do it 2 more times as we hack away at this polynomial and get it down to a quadratic by taking one off the power each time. Okay? So we run our synthetic division again. 2 comes down, negative 2, 3, negative 3, negative 5, 5, negative 6, 6, 0. It works again. So we've got our first 2 roots done. We'll go at it one more time over here. Negative 1, 2, 3, negative 5, negative 6. Again, this should work one more time. So negative 2, 1, negative 1, negative 6, 6. And finally we 0 out. So that is our multiplicity 3. So far we've just confirmed what they already told us, but really we've done all the work to get this reduced quadratic at the bottom here, which we can now write out as 2x squared plus x minus 6 equals 0. Okay? And we want this as a product of linear factors, so we know this should factor. That's going to be 2x, and I believe we want, that could be a 2 and a 3. Yeah, I think we'll go 2 here, 3 here, plus minus. So as a product of linear factors, this is x plus 1 cubed, 2x minus 3, x plus 2. If they asked us for the roots, we can actually complete all the roots. The remaining roots would be negative 2 and 3/2 as well if they needed that. Okay? But they actually just wanted the factored form, so we can give them that answer nice and simply here. So make sure you're up to date on your synthetic division, a good tool to have in your tool bag for these polynomial problems. Last example in this set of notes, we're given a power 4 polynomial with a missing coefficient. We're told that a is real, so we know we've got that conjugate pair idea. And we're given one root or one complex zero of p. Okay? Well, we can instantly write down another root, and we know that we have roots of 2i. We should also have negative 2i as a root as well. Okay? We're asked to find the value of a. We could go through all the synthetic division here. That's a little long. If we could just make the connection that when we substitute this 2i in the root we were given, we should get out a 0. So I believe if we just substitute this in and do a little bit of algebra with imaginary numbers, we should get a solvable equation that we can work with here. Okay? So we know this equates to 0 because that's a root. Okay? 2i all raised to the power 4, that should be 16i to the 4 minus 8i cubed. This will be minus 2 times 4i squared plus 2ai minus 24 should equal 0. I to the power 4 is 1. I to the power 3 is negative I. You can derive these by taking I squared squared. That is negative 1 squared, which is positive 1. Or even I squared times I. This is negative 1 times I, which is the I cubed. Okay? So simplifying this algebra now, we have 16 plus 8i, and then this would be plus 8, and then plus 2ai minus 24 equals 0. The real components should add up. So 16 plus 8 is 24. Those will cancel. And we have 8i plus 2ai should equal 0, giving us 2ai equals negative 8i. Leading us to the conclusion that a equals negative 4. Okay? So that's a nice algebra way to complete part A. Part B asks us for the remaining zeros. Okay? So we know we need 4 zeros. This is where we maybe wish we'd done the synthetic division here, but we can still go ahead and do that once we add a page here. Okay? So we have 1 0, 2 zeros found. We know that 2 of the zeros are 2i and negative 2i. So we have the full polynomial. We can run our synthetic division with the 2i. It's 1, negative 1, negative 2, negative 4, negative 24. And we can find our remaining zeros this way, just speeding through this synthetic division. 2i, negative 1 plus 2i, negative 1 plus 2i. Multiply that by 2i. That will give us negative 2i plus 4i squared. So negative 4 minus 2i can go right there. Add this. This will be negative 6 minus 2i. Multiply again by 2i. Lots of algebra work here. That will give us negative 12i minus 4i squared, so 4 minus 12i. And add that, that will give us a negative 12i. Multiply that, has to give us 24, which zeroes that out beautifully for us. If we use our other root, our negative 2i, we can do this synthetic division one more time to get us down to a quadratic expression here. So this is 1. This is negative 2i, this is minus 1, that is a 2i there, which gives us a negative 6, giving us a 12i, zeroing us out as we wanted. So we have x squared minus x minus 6 equals 0. Should factor up nicely. X, that would be a 3 and a 2, minus there, plus there. So our remaining zeros are x equals negative 2. 3, and the one we weren't given, which was the negative 2i. So a nice way to get all the roots of a polynomial bouncing between synthetic division and straight algebra. So hopefully you've enjoyed this video. In the next one, we will look at graphing complex numbers and something kind of called an Argand diagram and the complex plane.